What is the determinant? They throw this out at you and you can go through an entire linear algebra class with this bizarre and involved formula, but they don't explain it. They don't just tell you what it is, what it means, okay? So I'm going to try and do that for you, alright? Okay, so one great way to always try to understand something is look at some simple examples, okay? Look at some simple examples, see what it does to those, and then try to generalize from that, okay? So, and also look at examples that we have good, strong intuitions, okay? So let's just deal with a very simple kind of transformation, all right? Let's look at the example of where you're like taking like a square or something, all right? And you do some kind of transformation to it, and you get some other square out of it, okay? Let's do a very straightforward one. Let's do one where it doubles the width, okay? So this square becomes like this. Now, what kind of matrix doubles this width? Well, let's think about that. This would look like the following. If I had something like 1, 0 right here, so like this vector, that vector is now twice as long, right? It used to go out to 1, now it goes all the way out to 2. So it looks like 2, 0. Okay. And what happens when I put in this vertical vector? Stays the same, right? As in 1, 0 right here turned 2, 0. But 0, 1, the vertical one, just turned into 0, 1. Okay, so 2, 0, 1, this equals 0, 1. Okay, so what does that mean the matrix looks like? Well, let's think about this. If I put in A, B, C, D like that, I guess I'll use a more conventional way of doing it across the rows. So let's do A, B, C, D. So if I put in 1, 0 here, I get out AB, an AC, and that has to equal 2, 0. So A equals 2, C equals 0. So I know that this has to be 2, this has to equal 0, right? A equals 2, C equals 0, AC, like that. Okay? And also, what happens when I put in 0, 1? This looked like, let's see, A times 0, B times 1, so this is going to be B, C times 0, D times 1, like that. So this looks like 0, 1, right? I got 0, 1 out of that. So, okay, B equals 0, D equals 1. Okay, that's my matrix. That's my matrix for doubling the width. Alright? What's the determinant on that, alright? Well, the determinant, just so we're clear, the determinant of a matrix, A, B, C, D, looks like this. AD minus BC. Okay, so what would that look like here? Well, this would basically be, let's see, A times D, so that's 2 times 1, minus B times C, which is 0 times 0. So this is 2. Okay, that's straightforward. So, alright, how does this relate to the actual picture here? Let's see. I had a square which was 1 by 1. So this had area 1. And it went to another rectangle which was 2 by 1, which is area 2. So the area doubled, and the determinant was 2. Okay, that's, seems to be some kind of relationship there. Let's do another one. Let's do a rotation, okay? Let's do where I go from this square right here, and I turn it 90 degrees. Okay, so everything that was here is moved to there. Okay, so what does that look like? Well, that's basically going to be this guy. I'm not going to go through that whole process again. You guys can figure that out. This is basically going to be 0, 1, and then -1, 0. Actually, I'll just show you that works. So I put in 1, 0 right here. I get 0, 1, which is exactly what happens. Here's 1, 0, and then it gets turned to this vector right here, 0, 1. Alright? I have this vector right here, 0, 1, and this gets turned all the way over to here, to -1, 0. Okay? So, okay, this matrix makes sense. Alright, what's his determinant? What's his determinant? Well, let's see. I do determinant on 0, 1, -1, 0. And this looks like 0 times 0, right? A times D, and then minus B times C. So this is going to be 1. Let's see. So I had a square of area 1, and again a square of area 1. Okay, that's good. That makes sense. That seems to be some kind of, the area got preserved there. Here the area got doubled. Here the area was preserved. Let's do another guy. Let's just do another one where I have, again, my regular rectangle, and I decide to triple the height, 0, 3, and halve the width. Okay? That rectangle looks, that particular transformation, T, will be 3, 0, 0, well, excuse me, I reversed it. This should be 1/2, 3. This is pretty clear, it's going to be 3/2 plus 0, so 3/2. Which again, went from something of area 1 to something of area 3 times 1/2, 3/2. Okay, so this is making a lot of sense. Let's do one guy who's a little bit of a screwball and see what happens. Let's say I didn't rotate like I did over there, but instead, or do a length like this. Let's say I did a scale, okay, or a flip. Okay, so let's do the following guy. Let's say I have this rectangle, and I decide to flip him, like this, okay? So this part right here goes to here, then this part right here just stays the same, okay? So this part flips, this part stays the same, okay? One way of, let me make this actually perfectly clear. You can imagine that, oh, I have this picture right here of a guy waving, and now he's been flipped to a picture where he's waving with the opposite hand. Okay? Like that, okay? Opposite hand waving. That's what happened here. So what does that look like? That looks like -1, 0, 0, 1. What's the determinant on that matrix? It preserves the same area, right? Preserves the area, right? This box of area 1 to box of area 1. But if I do that, -1 times 1 minus 0 times 0, this is -1. Well, it's 1, you know, same magnitude, but it's negative. I guess that just means that it's because I flipped it, okay? Here, I didn't flip anything, alright? I just rotated it. I would have turned that picture of a man looking like this to a picture of a man on his side like this. Okay? Here, I actually flipped the whole image. So this is not just area we're looking at here, we're looking at signed area. So I'm basically starting to learn that with the determinant of a matrix equals is the scale factor. Or another way you could say is signed area. Okay? So if you double the area, then your determinant is 2. If you halve the area, your determinant is 1/2. If you flip the area, it's 1. If you if you flip the area, it's -1. If you rotate the area, it's 1. Okay? So that's what the determinant means. And let's just do let's do another example just to make this clear. Let's do the following guy. Let's do a scale. And what does a scale look like? What a scale is basically it takes this rectangle here, and then it just distorts it like this. Okay? And let me make sure that we're clear on like why that would work. This guy right here, 1, 0, he stays the same. But this guy up here, he changes. He goes from being 0, 1 to being, let's say, 2, 1. Okay? And the matrix that corresponds to is going to be 1, 0, 2, 1, like that. Now one thing here you should notice is, okay, this guy is area 1 obviously. How much area does this guy have? Let me redraw this out except a little more neatly. Okay, so base of 1. Let's write that out in a distorted way. So then goes out like that, and like that. Let's see. What's the area of a parallelogram? Because this is a parallelogram, right? This part and this part, the top and bottom parallel, the sides are parallel. The area will be basically the height times the width of the bottom. Okay? This says width of 1 and height of 1. So the area stayed the same. The area stayed the same. So when I take the determinant on that transformation right there, it's 1 times 1 minus 0 times 2, which is 1. Exactly the area, right? Exactly the scale factor. Things got pushed around, you know, like they did here, and things ended up in different places, but the area was preserved, okay? So the determinant keeps that in perspective, all right? Now let's do, so we have this understanding of what the determinant is. Let's look at one other example just so we're clear. All right? Let's say I had a different transformation than all of these guys right here. Let's say I had this guy. I had 2, 1, 4, 2. Okay? Let's look at what he does. So, alright, let's graph this out. Start off with, let's try and send this square. Okay? So what happens to 1, 0? Well, let's see. 2, 1, 4, 2, 1, 0. That's going to equal 2, 1. Okay. So, 2, 1. Right there. Yep, that's where this guy gets sent. Alright, what about 0, 1? 2, 1, 4, 2, 0, 1. That goes to 4, 2. Okay, where's that? It's like 4 and then 2 up. Oh, I don't really understand this. This is a little confusing to me. I don't see how this area gets into there. Let's see, let's do 1, 1 because I'm confused. That's going to look like that's going to look like 6, 3. Let's see, 6 and then 3. This is odd. 6, 3. I guess what's going on here is, all of this area right here collapses onto this line right here. Collapses onto there. So, let's see, I guess that means that the scale factor is 0, right? I send something that's of area 1 to something of area 0, right? What's the area of a line? Nothing. It has no area. So let's see here. Determinant of this guy, 2, 1, 4, 2. That's going to equal 2 times 2 minus 1 times 4. And that right there, 4 minus 4, that equals 0. That equals 0. So, this is what the determinant means. It has an incredibly straightforward definition. All it means is the scale factor. As in, if you had a square of area 1, what area will be the image of that square? Will it be the same? Will it be larger? Will it be smaller? Will it be nothing? 0. That's all the determinant is, and it is a sin, a vile crime, that they don't just say that outright. Because trust me, when we talk about linear dependence, this fact right here, that this square right here gets flattened, is essential. Is essential to understanding why that goes on, okay? So, okay.